And initially it was going to be released sometime in December, but apparently he got sick, had things kind of slowed down. So at this point, it's kind of unknown. But the power amplifier we're guessing released early as a module, quite cheap. And I bought one, and I feel like I saw the second one. And unfortunately, it's the same as the first. And I encountered TIARA, so I decided against using it. We'll discuss it today.
Did I put today's date, or did I get the type in 2018?
I expect a lot of people today because it's payday.
Payday.
Club.
Oh.
It's payday, so I was expecting a lot of people.
Payday.
Oh.
Real time. Only delay. It's working.
Worse.
Number one. Payday.
If I move to the two-call area, do I have to change my call sign? If I move to the two-call area, am I supposed to change my call sign? Or?
You /2 unless you want to change it, you get a second call, operator's call.
But I wondered, can I make my permanent location somewhere in 2 and not give up the 1?
You'll keep your operator's license.
So you want to keep 7J, right? So why did you use my address? Or keep the station as a mobile station?
Okay.
Actually, Paul Ryak in California is using my address for the JA call sign. So please feel free to use the address or use my clinic address or wherever you like.
Yeah, thank you very much for joining us today. Rick kindly proposed to present his home brew update. He is using also Hans Summer's kit. He will explain about that.
Some of them.
Summers.
Complete reports, right? Complete.
What, this? It's getting there. Now, are we expecting any more people, or should I just start?
We don't know because it's 7 o'clock is starting time.
Okay,
Some
so
member will come later.
okay, be good enough. We'll start then. Basically, FC1 is the name of my transceiver, and the first presentation I did here was March of 2017, and it was just a lot of metal work. You may remember. I had one update last year, and unfortunately, my attendance to the club has been kind of bad last year. A number of events happened. The company I work for was purchased by a U.S. company, and myself being a contract employee, I was in question whether I'd even have a job anymore. Late July, my first grandson was born. Finally, after all these years. Anyway, and I was working on this. So, today's date, let's see what we got. This is just an update. I was expecting a lot of people who may not have seen some of these. This is just a recap of the front panel. Basically, pops on, everything is enabled. There's a couple of unique things on this particular machine. Number one, I was talking to the gentleman earlier, this is designed specifically for CW. There's no sideband attempt at all. It also has an IF gain, which if anybody has used equipment that goes back to the so-called boat anchor era, in the late 50s, early 60s, a lot of receivers had IF gain, but you will never see it again. On the AGC, you'll also notice that there's an AF, RF, fast and slow. You can control, you have a lot of control over how the AGC acts. And there's also a CW DSP filter in it. But, so that's basically this, the front panel hasn't changed. This is the top of the receiver, looking down, the PA, receiver modules, the DDS VFO, and there's more stuff underneath here. It's a sub panel. Now, if we flip it over, there's a sub chassis here. If we turn it over, now we're looking at the bottom half, PA, front panel. This is the transmit module area, low pass filter, band pass filter, attenuator, PA driver, SWR detector, and this is the power supply area. Everything is shielded, everything is connected with SMA connectors and RG316 coax, everything. There's nothing left out in the open except the audio. And the audio was here. This is the audio amp. Basically, the audio is the only thing out in the open. Everything else is closed up. So this is kind of a recap of the, hopefully somebody can see it there, but of the block diagram. It has changed to some extent since I originally showed it to you. Although it's not really viewable here. Initially, all these little boxes were white. And as I completed a module, I would color them gray. So the only thing really left is the noise blanker. There's also another new addition. That's an AF preamp that I initially didn't have, but I added mid last year. These are kind of in yellow because they're finished. But what we're going to talk about today is the AGC, the PA's driver and key, and the PA itself. That's what we're going to talk about. It's a really straightforward circuit. It's signal conversion, 9 megahertz IF, very similar to the architecture of Drake and Swan back in the mid-60s. Very, very simple. Now, the AGC. Although I built the AGC board in mid-summer last year, I wound up throwing it away. The AGC turned out to be a 2.5-month effort. And I was really, I was stressed out with this AGC. I mean, couldn't believe a circuit could be so hard to get working correctly. It's really no mean feat. You really have to be careful. In my case, the AGC voltage is actually derived from two sources, the IF signal and the AF. So, well, the previous were flowing from two areas, we'll show it again. Secondly, we have independent control of the IF and AF attack and decay times. So, in combination, you've got actually 4 timing settings that you can play with. And each of them operate slightly different, and signals will, be according. AGC basically, and in conjunction with the S meter, is set so that S9 is 50 microvolts on the antenna. That is the standard. and just about any set you get that you buy nowadays will have 50 microvolts on the antenna at S9. Other than that, it's probably up in the air. If there is 50 microvolts on the antenna, and you were to go up 60 decibels, S9 plus 60, that means you have 50 millivolts on the antenna. Now that's a big signal. That's 50 millivolts of RF coming into the antenna. Next item is AGC action to start about S3. Now this is, I don't know if anybody's examined their commercial transceivers to see how the AGC actually operates. But most of them actually operate less than S1. AGC action will start. As a result, any background noise is actually, the background noise itself will actually operate the AGC and start pulling the signal down. And there are some other negatives too. Just as a matter of interest, because I belong to the ARRL, I have access to old QST articles. And there was an article in a 1948 QST. It was an advertisement by Collins about a receiver. And they stated something in there that, oh my goodness, it was from some microvolt area up to a huge 500 millivolts of RF, that their audio did not vary more than 1 decibel. And just, I was doing the AGC at the time, and it really caught me off guard. Wow, that's unbelievable. From that kind of level, all the way up to this huge RF, the audio remains constant. So I thought, well, I'll look at my icon and see what it does. I have a cheap icon, 7200. And believe it or not, it's constant too. From only less than a microvolt on the antenna up to 50 millivolts, the audio stays absolutely constant. Now that's being done by CPU, so they have a lot of room to maneuver. But there's a real downside to that. The downside is, and remember, their AGC, I'm sure Yaesu and whatever the other maker is, Kenwood, operate very similar. The AGC actually is working on the noise. So for example, if you're listening to CW, between the CW characters, the noise level itself is actually at the same level that the signal is. Because they're holding the audio constant, but between characters you get this whoosh, whoosh, whoosh of noise. And I noticed it on my icon even before I started building this. It was extremely annoying. It just, why am I getting this rush of noise all the time? But when I started to work on the AGC and tried to understand exactly what was happening, I figured it out. And that's one reason why I deliberately moved my AGC action up to about S3, S4. It's about S3 really. So, and the audio is not constant. If I have a strong signal up to a given level, it's much stronger than the noise. So it's really more pleasant to listen to be honest. The other thing is it's optimized for CW. The attack and decay times for CW are not the same as they are for sideband. Now, I'm sure on your present rigs, there's an AGC switch for fast and slow, right? But has anybody ever noticed that if you're in the CW mode, the fast and slow operates at a different speed than when you're in the sideband mode? What they've done is, and it's hidden, is they look at the mode you're operating in and they adjust the fast attack time and decay time based upon that mode. So from a user's point of view, you simply have fast and slow. But in reality, so there's a little bit of difference there. Now, here's something you won't see on any set here in Japan, or probably anyplace else. The S meter will work when the AGC is off. In other words, most cases, when you turn the AGC off, the S meter bars zoom over. If you manually change the RF gain or something, they'll go up and down. You have no idea what's happening. The reason for it is, quite simply, that their S meter voltage is being derived directly from the AGC voltage. So if you turn off the AGC, now there's nothing left to drive the meter. And in my case, it's different. AGC is turned on and off after the AGC circuit itself. Therefore, whether the AGC is on or off, from a user's point of view, internally, AGC is still operating. The meter is still working just like it always does. Now, lastly, one reason for the 2.5 months effort, AGC is a closed loop. It's like pushing jelly. Push here, it comes here. Push it here, and it comes up here. It is really a nightmare. Now, what in this 2.5 month encounter, or what kind of troubles did I have? Number one, probably the biggest thing here, my own ignorance at what to expect. I've never made an AGC before, never had to make one work, and I just didn't know what to expect. I just thought it was kind of like it goes in here and it comes out over here. And boy, that's sure not the case. I had gain distribution problems in the receiver. I had Chinese fake parts, and they drove me up a wall. Turned out I needed some additional test equipment that I had to test the AGC. Didn't have it. It wasn't available commercially. The gain curves in my RF stage and IF stage are different, super different. Basically, the RF drops semi-slowly, and then it'll have a knee and it'll go down quite rapidly. The IF actually goes down in a fair curve, so it gets to about 35 decibels, and then all of a sudden it's a hockey stick and goes back up again. And this is characteristic of the IF chip I used. You've only got one AGC voltage, and it has to satisfy both of these. And then to make it even worse, you've got a S meter, which has a log scale, but a linear movement that you have to match to a log curve. Because S units, dBs are in log. So there's a lot going on at the same time, really a lot. Now, the special equipment I made, or had to make, was what's called a ditter. It basically is an RF switch, and it's being driven by a 555 timer. And what it does, you put the RF in here, and due to the timing, it'll output a pulse. And a couple of issues here. You notice all these diodes in series. Those are pin diodes. And it requires 3 in series to get enough isolation between the on and the off. This has got approximately 80 decibels of isolation. In fact, it's got more leakage in the coax than comes through there. The other issue was the 555 timer. Most of these very inexpensive timers, you can vary the pulse or whatever, square wave if you want, by a timing capacitor or a pot. The hard part is varying the pulse width, the high, versus the pulse low. Usually they're not independent. And it took a lot of fooling around in some steering diodes here so that I could separate the charge and discharge path of the timing capacitor so that I could actually control how long a dot was versus the space between the dials. And this is what we came up with. Now this is a little hard to see. We're running very, very fast here, about 800 microseconds and milliseconds in pulse width. Here, let's see, 52 milliseconds. Here, 228 milliseconds. And I can vary the width or the period here, independent. Got two controls. And this is important when you're working on the AGC because you have to put a pulse into the AGC and see how it reacts. How fast is it come online? What's the decay time? How long does it take the AGC to recover? So a standard keyer won't work. But what it basically, I don't know if the data wasn't here or not. No, it's not. But basically, with the controls of the ditter, I can control the speed from about 6 words a minute to 68 words a minute. I can simulate CW dots at that speed. So that really was a big help, but it took a while to sort out. Now the loops. As I mentioned, this is a closed loop, and boy, it really gets nasty. With the RF amp coming in, we go to the IF amp. Off the IF amp, we pull an RF signal and put it into the AGC circuit. Same signal is going into the AF detector, and we pull AF out and also put it in the detector. One's going to control the attack time, one's going to control the decay time. And then, of course, we get the S meter here. Now, because of the devices I'm using, a dual gate MOSFET on the RF amp, and wideband video, actually it's a wideband video chip for the IF. Max gain for me is about 6.9 volts DC. Minimum gain, it's almost shut down, is about 1.2 volts. So it operates in kind of like a reverse of a vacuum tube AGC, which is positive going. So we got some sleepy people already. I think it's at 1. Okay. So this is actually the IF, the AGC circuit itself. And I know it's going to be a bit fuzzy. I had trouble getting a JPEG into the PowerPoint thing. Basically, there's a tuned amp, a pair of amplifiers afterwards, DC that amplify the RF, goes through a Schottky diode, is detected positive, and it drives an FET. There's a timing capacitor here and a 10 mega ohm resistor. This will determine the time for the IF portion. And as we continue on, we're now operating in DC, a couple of op amps, and a feedback loop. And we go to the AGC out and to the S meter. Now, there's some really screwy stuff going on here. There's also, which we'll see in the next slide, an AF amp coming off the detector that goes into these pair of diodes. So we got a full wave rectification, negative voltage that in essence is turning off this FET. When this is off, then this resistor is out of the circuit and the timing is solely here. When this is turned on, then this is a short. This small resistor then goes to ground, and we bypass the 10 meg resistor. Now, one thing to really just, here are the front panel controls for IF and AF, fast and slow. On this AF side, fast is basically taking this resistor to ground. Now this is inside the modules. This is on the front panel, same with this. Now, this worked okay, but this one didn't. Initially, it was a line off the bottom of this 10 microfarad capacitor, going to the front panel, to the switch to ground. This wire was unshielded. Now what happened was, I couldn't figure out why, the minute I hooked up this wire, my AGC voltage would go all over the place. It was strange. It would start operating, it would creep, it would do all kinds of strange things. Well, it turns out that this capacitor leg is extremely sensitive to noise, any kind of noise. Because it was floating, the noise itself got put onto the gate of the FET. So it was trying to change things. I finally wound up having to put a relay on the AGC board and make the switch right on the board. At that time, worked great. The other really strange thing you'll see, here's an op amp, and this is the normal feedback resistor, and the gain will be determined by this input versus this feedback resistor, the ratio. And I've got two LEDs, yellow LEDs, and a diode and a pot in parallel with that resistor. The purpose of that was to bend the AGC gain, bend the gain of this op amp, so that as it approached maximum AGC voltage, or the big huge signals, this would actually start to conduct, and it would change the gain of the op amp, thus bending. Instead of having a straight line down, it would bend it. There was a lot of strange stuff that I had to kind of sort out on the fly. But anyway, this, quite a bit of circuitry, had to go in a box this big, basically. We talked about the size of the box. This is the AF side. Takes it right off the detector, an amp, pot for the AGC hang level, and two op amps that are running pretty strong as far as gain is concerned. Actually, there's a gain of 10 in each, because it's 1K and 10K. What I'm looking for here is almost a square wave. You know, I don't care about the fidelity of the waveform. I'm driving an FET. As the audio becomes weaker, obviously the AF level becomes lower. Thus, it becomes harder to turn on and off the switch because of reduced voltage level. So I really need a big signal here to make the AGC operate down into the S3, S4, S5 area. So that was kind of interesting. All that circuitry is built here in this, with the exception of the AF. The AF, here's the detector, and here are those two op amps. There's a pair of op amps in here. But this is the AGC circuit itself and the relay. And I don't know, it may be hard to see, but in this little tiny area, we got the toroid tune circuit, one transistor, two transistors, three transistors, four. In other words, all the circuitry is piled in here. So in one hole, these perf boards, in some cases, there's actually 3 legs going in there, sharing the hole. I mean, I really stuffed it. But it worked, thankfully. Now, we'll see what happens. As I mentioned, the ditter puts out a pulse. Here's the AGC at just shy of about 7 volts. And a signal comes in, and we're not driving it all the way down, but it's a fair signal. very, very fast rise and fall time. And this is the AGC fast setting, IF fast. This is the test signal. So this is actually following fair. It's pretty close. This is real CW. This is taking a real CW signal. So you can see the CW signal, and there is some decay, even with this setting. The estimator will probably be bouncing from almost, 0 up to whatever level AGC is. If it was an S9, it'd be going from 0 to S9. It would be trying to follow the CW signal. Now, the next one, AF is still fast, but now we turn on IF slow. Here's the test signal. You can see the decay line is very pronounced. You can see the difference also. It's due to this slower decay. We get more decay in the real signal. So the estimator movement is going to not be so much anymore. Now we're going to go to an interesting one. Turn on AF slow, IF fast. Now here's maybe a weird signal, but this is actually the decay time of that capacitor in the AF side. And this is what you want to see. And this is what a real signal would look like. We're starting to see less AGC movement, and obviously the S meter is going to be, bobbing around about the signal level. Now we'll turn both on slow. Very long time here. The IF decay. Now look at the AGC, it's almost flat. In this case, you're listening to CW, the S meter is almost not moving. It's hanging right at the signal level, which, you have 4 different combinations you can play with. And depending upon the signal, there's advantages to using one or the other. It's kind of interesting to play with, actually. Now, excuse me. And next is the PAM. What am I going to do? 2 years ago, I bought this board from Australia. It's come from a company called Mini Kits, and they advertise it as a 16-watt sideband amp. Also bought Hans's QRP Labs 10-watt amp, which is going to be using in these QSX transceiver. You can see the size is really small. This one uses RF type FETs. Hans uses a switching type FET. I think it's on IRF 510 or something. So I bought 2 heat sinks. One I originally had, and I bought a second one. And I drilled both heat sinks and tapped them so that they would accept either board. Now, in this Mini Kits board, they use plus and minus, or plus 10 volts transmit, plus 10 volts receive, to switch pin diodes the receive path. So when you're in receive, there is a path out. In Hans's unit, it's up to you to do your switching. So I had to add a board here, anticipating adding relays. There's more to this story later, though. This becomes quite interesting. Anyway, I selected the Mini Kits amp for a couple of reasons. Number one, the Mini Kits has 45 decibels of gain. They have a MMIC amp in the front end. Hans advertises 26 decibels, but I could only see about 20. And I really didn't have enough drive when I was doing this, I thought he didn't have enough drive to run his at 10 watts. But something that was apparent very quickly, the mini kits has a much lower harmonic content. And it just was a matter of, well, one's got the RF path, receive path already enabled in it, built into it. It's got lower harmonic content, and that bothers me because of the 50 decibel spectrum in Japan. Another club I belong to, the Chu Amateur Radio Club, wants to submit this for Ham Fair next year. The homebrew thing. Now, to be accepted, and I've learned firsthand this is what happens, to be accepted, if it's a transceiver or a transmitter, it has to pass the JARD specs before it will be allowed to be an entry. So if this is a possible candidate for Ham Fair next year, I've got to be below 50 decibels in harmonic level. So that was the choice I made. Now, here's the PA itself. Now, we're talking about the mini kits one. I'm actually able to push it to 20 watts, 13 volts in DC. Power out's 20 watts. The harmonic at this power is about minus 40 decibels. Now, that just about passes the US spec, 43, but it won't pass the Japanese spec, 50. Now, if I back the power down to anywhere from 10 to 12 watts, I can't see any more harmonics. They're more than likely below 50 decibels. I mean, my FFT, as we're going to see, is a arithmetic type FFT. It's not a real spectrum analyzer, so I've got a lot of ground noise or hash. This, by the way, it's something I picked up at Ham Fair last year for 3,000 yen. And I did a refurbish and recalibrated it. It's actually quite an interesting SWR meter. It's got 3 inputs. You can actually select 3 inputs. You have 2 for HF, VHF, and then 1 for UHF with an N connectors on it. Pretty interesting. Big meter. I added the light to it. So, looking at that particular output, here's 17 watts. In fact, we've got 82 volts now on the dummy load. And this is the sine wave. This is what it looks like at 17 watts. This is 15 watts, 74 volts peak on the dummy load. Now, proof of the pudding is here. CFFT, here's the signal. This line here is minus 51 decibels. And this is basically scope noise. I honestly don't know. This is 15 watts. I don't know where the harmonic level is. It's got to be below 50 decibels. I hope. I don't know how good. There's spikes here, but this is not frequency related. You turn the time base and they come and go. So they're strange. So I think I can pass the spec. Now, here's something caught me off guard a few days ago. I mentioned there was a receive path on the board, switched with pin diodes. Their manufacturer in Australia gave a spec of, on the receive path, there was 1 decibel or less loss. So I wanted to really make sure that that was the case. I didn't want to put all this thing together and then find out I had, 3 decibels, 4 decibels of loss through their diode system. Anyway, this is what happened. Those are 800 millivolt spikes on the receive line every time you make a switch from transmit to receive. Now that's bad news. In other words, these 800 millivolt spikes are being pushed right into your RF amp. And I'm sure the RF amp is not going to be too pleased with it. So, the loss was pretty close to their specs. It was about 1 decibel, actually less, which I thought was pretty good, except for the spikes, which means you can't use that. So, onboard switching was gone. I was relegated to go with relays. And we'll come back to that a little bit later on. But what it basically shows is test everything. Don't take anything for granted. Of course, you wouldn't take your own work for granted, but even a board maker or a module maker or whatever else, they're selling something and it's a spec, but you better check it. This was really a disappointment. I don't know how they get away with it, but anyway. Now, talk about the PA driver. I intentionally did the PA first because I could tell, like from the data, I would know how much RF would be required to run it at 15 watts. So, PA was done first, now we're back to the driver. This is the last module, major module of the transceiver. Some of the requirements were an independent power level and ALC control. In other words, I want to be able to vary the power, but I also wanted another way to vary the level based upon, let's say, a tune switch or SWR detection. So those had to be separate. I wanted a 2 to 4 millisecond rise and fall times on the keyed waveform. That's really important. A lot of times, this rise and fall time will make a difference whether you make a QSO or you don't. Anything faster and it sounds hard and clicky. If it's slower, you have a very soft keying, and with weak conditions, you just won't be heard. They gotta come back and ask you QRZ, QRZ, QRZ. Most rigs, Yaesu, ICOM, will run about 4 milliseconds. But they all have problems, another set of problems. And this, invariably, their first dot, when they make their full break-in or semi-break-in switch, the first dot will be shortened. In fact, it's so bad sometimes, you listen on the air, you can't even hear a J, you hear an O, because the first dot is clipped. Now mine, on my QSK unit or module timing stuff, logic, I knew this could happen, and I intentionally moved the key stream X number of milliseconds so that there's no way that I can have a shortened first character. But this is another issue. This is turning the RF on and off. The other question I had was, did I have enough drive from my DDS to run one of these things? Another issue, when you vary the frequency, does the level stay constant? And the reason that question came up is PA driver drives, in fact, it's Hans, one of his bandpass filters. So the bandpass filter response, could be a little bit wacky as far as input and output impedances. So I had to make sure, and we'll get to that too. Another issue, signal blow-by has to be greater than 75 decibels. What do I mean by blow-by? Blow-by is basically the signal between the characters. In other words, your VFO is putting out the same signal all the time. And at some point, you're flipping a switch. Normally it'd be a transistor. So when the switch is off, theoretically, there's no leakage, but that's not the case in the real world. There will be leakage. So it could be that between characters, you hear a faint carrier underneath, and that's low-fi, and that's really a no-no. You don't want that if you can help it. And lastly, even worse than the HEC, this has to fit in a smaller box. It was only about, actually it's 27 millimeters by 36 millimeters in size. So here's the driver schematic. This is the guy that really does a lot of work here. This is an integrator. The key itself is driven from logic. The key turns on and off this transistor. There are C and R, the charge and discharge. So it's an integrator, charging and discharging. So it's not straight up and down. And then we basically have, from the DDS, an amp that is being keyed. Its DC is coming from this transistor. So when this transistor is on, 10 volts appears on the collector. It also provides bias to this base. When it's off, no voltage, and the bias goes down. Have another amp. This controls the level, controls the amount of current through here. Then we go to a variable attenuator. This is where the ALC does its operation. It's a simple transistor driving, or not driving, but controlling a pair of J310 FETs. And then we go through the bifilar coil. And the DC is actually comes from here also. Now, here comes the interesting part. When I first, it seemed to be working pretty good. And when I tested the frequency versus level, I found that I had my level up at about 6.8 megahertz. Nice. But when I got to 40 meters, it started to drop down. I had a peak. Well, the only thing that can cause that is the bandpass filter. Now, obviously, the bandpass filter was designed for 50 ohm input, and this wasn't. So what I did was, I put a 6 decibel pad in here so that the bandpass filter would see only 50 ohms. Voila! Now I got a nice flat output across the entire 40 meter band. The other question of, do I have enough drive from the DDS? I actually had overkill. I had huge amounts of drive. I've got a 28 decibel pad in front of this. So I'm attenuating the DDS signal by 28 decibels before it even gets to here. So I've got gain more than I can use, which is it's better than the other way around. Interesting thing here is, these are FET or SMDs. Now again, I said I had to mount this in a super small board. And at this point in the game, there are no more options. I can't just throw in an extra module or increase the size of the module. It's cast in iron. So what do we do? Well, start to make a small board. The board itself is 27 by 36. Now the module itself has got three millimeter screws, but I would imagine this is close to 5 millimeters in diameter. Hicks studs inside to fasten the top. Get SMA connectors here that I have to clear when I put this in. So I had to notch this out. So this is the working area. Oops. That one. For this entire circuit. And it left me head scratching. So I had some SMD capacitors. This thing takes a lot of bypass capacitors. I had 0.1 and 0.01s. Also had the SMD FETs. By chance, 6 months ago in Akihabara, I run across a 6 decibel Panasonic attenuator chip. So I bought them. But I look at it and wow, these are really small, really small. The chip is here. It's 1.5 millimeters by 1 millimeter and has 4 legs on it. There's a 0.01 cap here. So I really struggled, didn't drink any coffee one morning, and I soldered it in there. If you drink any coffee, you'll never get one of these things in. And I put 2 of them onto the rug with the tweezers. Trying to hold it down. It was ping, and they were gone. Never found them again. So anyway, on this little tiny board, I have a 6 decibel attenuator, and I tested it. My gosh, it works. So here it is, and it's standing upright. JFETs are mounted on breakout boards back to back. Here's the output toroid. This is a control transistor. Now, here you'll see SMDs mounted in a relatively strange way. Are sitting about 45 degrees. Normally, the SMDs are mounted on printed circuit little pads. But I used Manhattan style. And previously, in some of the other modules, Manhattan style, these little islands are 1.6 millimeter single layer boards that I nibble and get little chips out of. But with 1.6 millimeters, I couldn't attach an SMD chip. So I don't know where I got it, but I have some sheets of double-sided copper board, the fiberglass boards, and it's only 1 millimeter thick. So what I did was, rather than epoxying to the board, I pre-coated the board with solder, and then pinned the back of the island and then sweat soldered it on. So that means the islands are only 1 millimeter high, and you can actually put a relatively large SMD chip on 45 degrees and solder it in. So that's what I did. And they're all over the thing. So, excuse me, end result, it all fit in a little tiny area. Here's the attenuator, the toroid that we saw earlier, the 2 JFETs. Here's one of the 2222 amps, the input toroid, and the key stage. And then I have ALC pads and AGs, or key 10 volts and ALC. These are coming from feed-through capacitors from the outside. When the DDS goes in, and then it goes to the attenuator now. And it actually works. And unbelievably, it worked the first time. Well, I prototyped it quite a bit. I don't know if that, maybe I just jumped over it. So what are the results? Basically, level control, the pot, I can vary the output from 100 milliwatts to 20 watts. The ALC works on a range of 2.2 to 1 volt. When you change the source voltage of the FETs, this is the span you work with, and basically that'll vary the output by about 45, 50 decibels, more than enough. Blow by, let's say minus 80 decibels at 15 watts. Blow by is interesting because the stages are turned off. So, blow by level is totally independent of power out. It's there. This is what it just slips through. Initially, it was 200 millivolts. And that is bad, really bad. And what happened was, go back to the circuit here. Initially, this circuit had a feedback path of a resistor and a capacitor here for, leveling of the output versus frequency. And this was tied to the 10 volts directly. The biggest culprit was this silly feedback path. When this was off, RF was coming right through here, through the feedback path, and going right to the amp. The amp has the bias turned on. It's waiting to amplify anything it gets to, and it certainly did. So I removed this and also keyed this stage, and now the blow-by is 8 millivolts peak to peak. Now, when you compare 8 millivolts peak to peak against 80 some odd volts coming out, or 70 some odd volts, it's good. Can't hear anything. Power versus frequency is flat from 6.9 to about 7.4 megahertz. Rise time 2 milliseconds, fall time 2.8 milliseconds. Right on the money. Now, proof though is in the pudding. We'll be seeing some data information here. The top trace is basically the plus 10 volts transmit. In other words, I have a transmit and receive, they switch back and forth. So when you go into transmit mode, 10 volts VT is turned on, 10 volts VR is turned off. So looks like that. So here it's turned on. At this point, bias is applied to the PAs. It's ready to go. Now, receive to transmit change. This is RF out of the PA itself. 8.6 milliseconds, there's no RF. And that's intentional because they're closed relays. So that's part of the effort of slipping the key string in the logic area. So between the bias applied and the RF, I've got 8 milliseconds of freedom to play with, which not bad. Now, in this one, very similar. This is RF out of the PA, semi-break-in. Transmit is turned on, turned off, turned on and off. Now, question is, what's this? This is a semi-break-in timeout. When I use semi-break-in, I set my timeout for about 450 milliseconds. That's what I'm very comfortable with. So you can actually see it is working. After the keying stops, it waits 455 milliseconds before we're switched into the receive mode. So it's working exactly as expected. Now here's another interesting one. This is, again, very similar. I've expanded here somewhat. This is the RF coming out. You can see it start to rise until it's full scale or full level. This is 2.1 milliseconds. Again, perfect. It's a little fast if you're running 100, 200 watts, but for 25, 10, 15, 25 watts, it's pretty good because you're going to be weak anyway. And it's good. It's better to have a little bit of a hard CW rather than a soft. So now, we talked about the integrator working, the key 10 volts, charges and discharges. What we're seeing here is the key 10 volts. So it's off. It's time to go to transmit. Well, we're actually in transmit mode. The integrator charges up, and now we get 10 volts out. It turns on the RF. So we get our nice little slope. That's what controls, the integrator is what controls the rise and fall time of the RF. So here's the fall time, here's the integrator discharging, and here's the fall time. It's 2.75 milliseconds. So it's not bad. I've seen worse. There's no overshoot. It's a very clean disappearance of the signal. So that's pretty good. Now, present status. The AGC is working super good. Mode switch, QSK is working okay. Sensitivity of the receiver is the same or better than my ICOM 7200, and it's 0.02 microvolts. It's really minus 130 some odd decibels. On the AGC, I have less pumping than the ICOM. The ICOM picks their AGC off very soon after their higher frequency roofing filters. So the bandwidth is quite wide. As a result, any adjacent stations will actually cause the AGC to operate, which you don't want. Now, my AGC is operating after 600 hertz crystal filter. So I don't get as much pumping. In November, Shoe City had their Bukanahi celebration, and our club, the club I belong to there, the Shoe Club, they have a homebrew section, and it won first prize. Basically because I was under pressure to have something operational for the culture day, even though I finished the AGC in September, I put the covers on it and put it in its actual area and operated it for an entire month to see how it compared under a variety of conditions with the ICOM. And it does well for itself. Unfortunately, in November, we had a lot of OTH radar. You're familiar with it? I mean, it's really a bugger. That thing is like a sawtooth, and even noise blanker won't operate with it. So both rigs have trouble. I can actually, my experience with playing with it was, if I turn my AGC off, back down the IF gain, and crank up the DSP filter to about 100 hertz, I could actually copy a signal better than I could with the 7200. So I was kind of surprised, but generally speaking, the noise blanker in 7200 is super. The noise reduction feature is great. So anyway, the receiver just worked right along, and now the transmitter is ready to go. So, ELC, SWR, noise blanker. I'm not in a rush on these. The SWR, if your rig is running 100 watts, 200 watts, the SWR protection is super. This thing's only running 10 watts. Normally it's pre-tuned, so I'm not too worried about it. Noise blanker, I'll get to it in time. Today is what, the 18th? I will have, well, I hopefully have my first QSO on the rig by the end of this month. Unfortunately, I blew up the PA. Well, it was my own stupid fault. We go back here a bit. The PA. Oh, this is something again. Take note of that, because we're going to see something here very soon. PA. Let's see, okay. The PA, there's a header that goes here, and theoretically, you supply or receive 10 volts or transmit 10 volts, push to talk, etc. It has develops bias for the FETs here, and there's some surface mount MOSFET underneath. It's a P channel, which is rather uncommon. And I had spaghetti all over the place and clips and whatever. And what I apparently did was shorted out the bias line and popped the transistor. So the PA itself works, it's just that the bias is a little bit sick. So basically, that's it. Now, there's one thing I'd like to show, if I can. Remember those spikes. I can get this seem to work. Let's see. The two independent JPEGs. Okay, this is a good one. I don't know how it would come up. It's got this Windows thing. Oh, it does work pretty good. These are, the scope I have has a USB port to it, and you can save your data, which is good. I took out a lot of components for the so-called receive line, and I installed two double throw relays for send and receive. A lot of QRP rigs use a single one and just quickly switch between the send and receive, but I wanted independent input and output for isolation's sake. So the question was, does this thing work? So what I did was, I took the DDS output, I plugged it into the PA, its output. So I have DDS voltage running into the PA, simulating a received signal. Now, the DDS, because of the 9 megahertz IF, runs at 16 megahertz receive. This is what we're seeing. This is 16 megahertz. Now we go to transmit. Initially, this threw me for a loop yesterday, but boom, we get this. This is 7 megahertz. In other words, the DDS, as soon as you switch voltages, it'll immediately go from send to receive, and it'll switch frequencies really, really fast. So that's what happens. When I saw this, oh, this is good. This is supposed to be the receive line. Turns out, this width is 2.25 milliseconds. Now that is the closure time of the relay. So the relay's voltage and its arms actually close at 2.2 milliseconds. Spec is 3 milliseconds. But they're 12-volt relays, and I'm running them at 10, so I expected it to be, but no, not. It's extremely good. Now there's one more that I have. It looks the same. Remember earlier when there was a graph showing when the RF appeared out of the PA, and it was 8 milliseconds. And I mentioned at the time, well, that's time for the relays to close. And sure enough, here's the antenna relays actually closing in 2 milliseconds or 2.2 milliseconds. RF will appear here in transmit mode at about the 8 millisecond point. So I have time to spare. So no spikes. Nice and clean. And that kind of wraps it up. I've ordered my MOSFETs from Australia because they're kind of a weird, off-the-wall FET. They haven't arrived yet, but I expect them next week. It's ready to go. I mean, I noticed Hans' QRP rig does too. The heat sink does really get hot, especially if you hold the key down for an extended length of time. So what I did was, my heatsink is 8 centimeters in width, and just by chance, they sell an 8 centimeter by 15 millimeter muffin fan. So it's exactly the same width as my heatsink. So I strapped it on there. So I have a fan mounted now on the back of my heatsink that pulls air through the heatsink area. And it seems to work pretty good. Everything else is modules waiting to be put back together. Again, though, it's verified. As soon as I re-verify the okay, make sure it does what it's supposed to be doing. Put it on the air. See what happens. But it's been an experience these last 2 years. Certainly an educational experience.
What class is the amplifier?
It's been running in Class A. Hans amp, it's either A or AB, I'm not real sure, but due to the difference in FETs, he's got about 125 milliamps of bias on each FET. So when you look at the current, idling current, it's about 250 milliamps. Plus he's got some transistor effect drivers. They take about 60 milliamps. This particular one is running 500 milliamps per transistor. So it's running an amp idling. It's running a solid Class A. Now I could, theoretically, back it down to a Class AB or even, God help, a C class, but I wouldn't want to imagine what the harmonics come out. And I just, at this point, and with the Japanese spec of 50 decibels, I just can't afford it. The transistors have plenty of heat sink. It's actually fan cooled, and they can run fine, no problem. Now I did notice that ICOM, I was curious, I know, wow, this is a lot of current. When the minute you push the torque down on the ICOM, it goes up to, mine goes up to about 4 amps. It'll go from a little less than an amp up to 4 amps or more. So they've got a lot of current running too. They probably got 500, 600, 700 milliamps, maybe even an amp of idling current to theirs, which is about what you would expect for a 100 watt pair. So I'll tell you though, without a scope, they never get this far. Never. That was the best investment I ever made. And they're cheap. They're silly cheap. This thing cost, you know, buy it, 40,000. Yeah, they're Chinese, but they're all about the same. 200 megahertz bandwidth at 1 or 2 gig sampling. It's got the arithmetic FFT. It's not without its issues, but for that price, and you can't go wrong. And it certainly allows you to find out what's happening. I never would have sorted that AGC out without it. But that thing drove me up a wall. I threatened to throw the whole thing in the garbage can more than once. But
So overall, what's your power consumption? Like receive and transmit?
to be honest, I really don't know.
Okay.
I mean, because I've had the receiver online, and it's about an amp maybe. I mean, I've got a rather healthy audio amp.
Mm-hmm.
I haven't had both halves working together,
Okay.
so I really don't know. But on my bench power supply, I made up a pigtail with some connectors, and I put a connector in so that I could put an ammeter on there.
Mm-hmm.
Oh, that was an ammeter. I blew mine up. Well, in final fall, I just didn't even think. On my meter, which is a sound meter, it said 600 milliamps or something, one setting, and then if you want to go above that, there's a whole different banana plug. You have to switch it over. I thought, well, 600 milliamps is no problem. But I hadn't thought about the surge, when it turns on. And I don't know what did I do? So I opened it up, and here's a strange, extremely strange ceramic fuse. What do I do here? So I looked on eBay, and by golly, they had them. So I ordered them, so I can blow it up another time, so there's some fuses. But I have the ability to measure the current, both receive, idle transmit, full power transmit, and I'll get that data later. But I would, right now, at 20 watts, it's about, PA draws about 4.2 amps. So at 12, 15 watts, I don't know, it's 3.5 something in that neighborhood, it's 3 something maybe. So to be honest, that's going to be worst case. The RF chain itself for the transmitter is basically the DDS, PA driver, and the amp. There's no strange stuff. The reason being is that the DDS, it has an RIT facility in it. I mean, I bought it, from a guy in Nevada, the DDS, and it has an RIT function. Well, the RIT function can actually do plus or minus 9 megahertz, and it is very, very fast switching. So what I did was, I set the RIT frequency to be the same as my IF. So I can go from turning an RIT on, and actually will become 7 megahertz. It becomes my transmit frequency. And it goes back to the receive mode, it goes back to 16 megahertz. The DDS drives the PA driver, the PA driver drives the PA itself. When I was the PA driver doesn't take, 100 milliamps at worst case. So I would say, of course, receive and transmit are not be going at the same time. Worst case, 20 watts, about 4.2 or 3 amps transmit. Receive maybe 1 amp, 1.5 amps worst case. So it was supposed to be portable, but the bugger weighs 6 kilograms. It'll actually fit in my rucksack if you got to pull it. I mean, it didn't turn out to be too portable. But it sure is fun. I mean, I'm sure it's going to be a thrill to get a QSO on something you made yourself. I know I had a big thrill when I first got my first QSO on Hans's QCX transceiver, the QRP guy. And it's done itself really proud. It's one of the few QCX rigs that actually entered the ARRL DX contest. That's a rough contest for us because we can only contact them. It's not worldwide DX. So anyway, and that is all, gentlemen. That's the end of the story. Unfortunately, due to its size and my age, I will not be bringing the item to the club for perusal.